Good morning, everyone. Today I'm going to talk about the most exciting developments in software engineering, how we are using artificial intelligence to transform code at massive scale, far beyond simple autocomplete suggestions to intelligent device transformation. We are living in a pivotal moment. Developers have traditionally relied on line by line tools and manual refactoring for large changes. What if we could use AI for doing entire package migrations? Build and bug fixing, which involves automated error resolutions, code refactoring, structural improvements, maintaining a specific behavior, fixing code style issues, enforcing a standards automatically, static analysis based repairs, fixing linter or analyzer warnings, static analysis annotations such as adding type hints or documenting. Let me show you how we're actually using AI powered large scale code transformations. Before we talk about solution, let's understand the core problems we're trying to solve. There are three fundamental challenges that prevent standard LLMs from handling large-scale transformations effectively. First, context window limitations. Here's the reality. Most code bases are massive. You can't fit an entire repository in a single LLM API call. We need to break the code base into intelligent chunks and orchestrate multiple LLM calls, each with the right context. This requires sophisticated mechanism that understand software structure, not just splitting code randomly at character boundaries. Problem 2, knowledge cutoff. LLM are trained up to a certain date. If your code bases use a library that was updated yesterday, the model wouldn't know about it. This is especially critical in programming where API changes happen frequently, and outdated knowledge can lead to incorrect solutions. Problem 3, hallucinations. LMs are fantastic at generating code that looks code syntactically correct, but they're also prone to making things up, using APIs that don't exist and ignoring edge cases or implementing logic that seems reasonable, but it is fundamentally flawed. For critical transformations, this is unacceptable. These three challenges mean that LLMs alone, even powerful ones, simply cannot reliably handle repository scale code transformations without human interventions at every step. Here enters code plan. Code plan is basically a symbolic framework that combines the creative power of large language models with the rigor and precision of traditional symbolic reasoning and static analysis. What does code plan do? It automates large interdependent code changes. Think package migrations across your code base, multiple file refactorings, or modernizing legacy code. The key innovation here is treating repository level coding as a planning problem, not just a generation problem. Code Plan integrates LLM with intelligent planning. It doesn't just generate code, it reasons about what needs to happen, breaks it into steps, validates those steps, and orchestrates the execution. Some real use cases are C sharp package migrations across your entire code repository, Python dependency updates that touch multiple services, static analysis driven repairs when you're fixing violations or compliance issues, adding type annotations to untyped code at scale. CodePlan is extensible. It's built on modules and transformations, actions and prompts that you can customize for your specific in software engineering tasks. CodePlan at a high level is a symbolic framework for building AI-powered software development workflows for inner and outer loops for software engineering. It integrates the power of LMMs with intelligent planning for tackling complex coding tasks that cannot be solved using LLMs alone. It basically combines the power of LLM and symbolic static analysis approaches. Okay, let me walk you through what how code plan actually works. The architecture has majorly three components: input, code plan engine, and the output. The input basically consists of your code repository or directory, knowledge-based repositories with precise transformation instructions and examples, static analysis reports and logs that identify issues. The code plan engine consists of four major aspects. Prompt context. The first, prompts contextualization. Before we pass, before we ask anything to the LM, we carefully prepare prompts with most relevant context. This is crucial. Bad context can lead to bad outputs. Second, Planning and orchestration. Complex transformations aren't one-shot operations. Code plan breaks them into structured steps and coordinates the execution, making decisions about which tools to use and in what order. Dependency analysis using AST. We parse your code using abstract syntax trees, a representation that captures the actual structure of your code, not just the text. This lets us understand the relationship between the different components. Static analysis. We validate the transformations and use static analysis to guide them. Is this transformation correct? Did we break any builds or unit tests? Will it break any downstream dependencies? Stack analysis gives us the confidence. And finally, the output is basically the transfer generated code ready to be integrated. Here's a walkthrough of the architecture diagram. On the left side, as you can see, the inputs consist of the code repository, the knowledge base repo, or the instructions. The static analysis allows for verifying or for performing static analytics based transformations. The main engine consists of prompt contextualization, planning orchestration, dependency analysis, which uses abstract syntax trees, static analysis validation, and the LLM. And on the right side, the generated code is the output code which gets generated, transforming your repository. At a high level, technical magic which happens in code plan majorly consists of three techniques. LLM planning. Instead of asking an LLM to solve a problem in one shot, we asked it to plan. Break the complex task into structured steps. Choose which tools and techniques to use. Decide the order of execution. This enables the goal directed execution rather than hopping on a general purpose model gets it right. AST based chunking. We don't split the code at arbitrary character positions. We use AST which is abstract syntax trees, to identify meaningful boundaries, function classes, loops. Each chunk remains syntactically valid on its own. This produces better embeddings, better retrieval, and more accurate LLM responses. RAG, the retrieval augmented generation. A RAG basically consists of a retriever and a generator. The retriever finds relevant chunks from your knowledge base and instructions and the code base. And the LLM generator basically integrates the context into its responses. This combination basically reduces the hallucinations, overcomes the context length limitations, and incorporates fresh knowledge into the training data. Together, these techniques create a powerful system for handling repository scale transformations. Okay, now let's go deeper into the abstract syntax trees as well as the RAG. Okay, let's walk through an EST concrete with an example. So here's a simple Python code, a function that greets someone. When we pass this AST with AST parser, we get a hierarchical tree structure. At the top is a function def node. Under that, we have the function name greet, the argument's name, and the return statement. The return statement contains a binary operation, which is string concatenation, combining hello with the variable name. Now, this might seem like a minor detail, but it's transformative. When an LLM sees the structured representation instead of raw text, it understands the code at a much deeper level. It knows these are distinct semantic components. It can reason about how changing one part affects the others. This structure enables meaningful code chunking for LLM processing and accurate relationship between the different components. LLMs see code as plain text. It's just a sequence of characters. They don't inherently understand the function is different from a loop, that a variable declaration is different from a function call. They make educated guesses based on statistical patterns. This leads to generic inaccurate responses and potential hallucinations. The AST solution breaks the code into organized hierarchical representation. Now the LLM can understand methods, properties, arguments, data types, and logic flow. It sees the skeleton of your program. This makes the AI responses far more accurate and insightful. When you feed an LLM an AST instead of raw text, you're given a semantic understanding layer. That's the major difference between a generic tool and a specialized tool. Okay. Next, chunking. Now we're going to look at the two approaches for breaking the code into chunks. The first one is traditional, and the next one is AST-based chunking. Traditional character-based trunking treats code like any other text. You might split at 500 characters or 1000 characters. Here's what happens. You end up cutting through middle of functions. A function definition gets split across chunks. An inclusive statement sits alone. The semicolon statement that closes a statement might be in the next chunk. The code structure is disregarded. You get malformed, syntactically invalid fragments. Statements lack proper syntax closure. The semantic meaning is completely destroyed. An LLM asked to process these fragments would get completely confused. It's like asking someone to understand a sequence broken randomly across lines. Next, now let's see how AST-based chunking significantly improves our use case. Each chunk represents a code boundary. The preprocessor include is its own chunk. The using declaration is its own chunk. The complete functions are preserved as a single chunk. This, which makes more sense and provides better understanding to the LLM. The code is split at meaningful boundaries, functions, control structures, usings, declarations, etc. Each chunk is syntactically valid and complete. Semantic integration is completely preserved. When an LLM receives syntactically valid code that represents semantic boundaries, it can generate better confirmation. There is no guessing about context that was cut off. The model understands the complete picture of that chunk. This is a foundational technique which we use for enabling repository scale transformation. The planning along with the AST analysis helps us split the task into meaningful sections and loop or iterate over the LLM calls, providing meaningful chunks of the AST again and again. Next, we're going to look at retrieval augmented generation. We use RAG majorly for two major aspects, knowledge cutoff and hallucination problems. RAG has two simple components. The retriever searches through your knowledge base, documentation, examples, existing code, best practices, majorly trying to understand what is the transformation you're trying to achieve. It uses the retriever. It uses a retrieved documentation, combines it with the AST-based chunking, and provides it to the generator. The generator takes whatever the retriever found and processes it through an LLM. The model integrates this fresh, up-to-date context into its response. The beauty of this approach is that the LLM has current information about your specific APIs, frameworks, and patterns. It's not operating on the general knowledge from its training data. It's operating on the actual code base and the knowledge base of instructions which we provided to it. This combination dramatically reduces hallucinations, overcomes context length limitations, and ensures your transforms use latest frameworks and the best practices from your organization. Okay, let's talk about real world impact. First, time savings. Organizations doing mainframe migrations have seen 70% reduction in modernization timelines. Tasks that used to take 3 to 5 years are completely automated. Quality improvements. Code plan, because it integrates with a feedback loop with static analysis, the transformations are completely valid and preserves the original behavior. There are fewer manual errors in large-scale transformations, higher confidence in the results. Developer productivity. Developers are freed from repetitive, error-prone tasks, allows focus on high-value architecture and design work, enables non-experts to perform code transformations as well. Enterprise applications. Packet transformations across hundreds of files, hundreds of repositories. Legacy code modernization. Compliance and security updates at scale. These are real use cases delivering real business value today. Future and challenges. We need to be honest about the current limitations. Context length still limits extremely large code bases. Some code bases are simply enormous. Model hallucinations is not completely disappeared. They're reduced, but validation is still essential. Repository scale analysis is computationally heavy. It's not free. Complexity in handling dynamic languages such as Python and JavaScript is higher, as we struggle with this traditional static analysis with them. Emerging trends. One of the biggest emerging trends is multi-agent systems, where multiple specialized agents have the different parts of transformation. continuously learning from developer feedback as to how developers modify its output. Integration with actual development tools such as your IDE, CI/CD pipelines, not just standalone processing. I would like to conclude with some key takeaways. First, we are moving from a line by line autocomplete to a repository wide reasoning, from simple text generation to structured planning with validation. Neural approaches are pure LLM based on neural approaches are being integrated and made neurosymbolic hybrid systems that combine the best of both worlds. Planning frameworks that decompose complex tasks, AST based understanding, multi context integration are some of the main aspects which are enabling this transformation. Bottom line, AI powered large code transformations are no longer a theoretical or distant future. They are achieving production ready results on real world repositories right now. This technology is transforming what's possible in software engineering. We're not replacing software developers. We're amplifying or enabling them to achieve more. We are automatically we are automating what's repetitive and error prone so that they can focus on what's creative and strategic. The future of software engineering is at repository scale, intelligent planning and powered by AI. Thank you.